Have you ever been waiting for something to download and it gives you the time left to download and it says estimated time remaining, 3 minutes and then 5 hours and then 2 minutes and then 15 seconds and then 6 hours and then 2 minutes. And you're like, what's going on? How could it possibly jump around that much? Well, today we're going to talk about the physics equivalent of that. The reason that goes that way is that the computer is taking the amount of stuff left to download and dividing by your current download rate, which of course varies from moment to moment. And so the time left will vary from moment to moment. In physics, this will represent itself through things like instantaneous velocity. As we've seen, velocity need not be constant. Sort of duh. Average velocity is easy to compute, but it's not particularly useful. It depends on the start and end of your interval that you pick, but essentially acts as if your velocity were constant. But you know that your velocity can vary. Imagine that you're driving home today after class and a friend calls you. You don't pick up, you shouldn't answer phone calls while you're driving, but your passenger does answer, and the friend asks, "How fast are you going?" You wouldn't say, "Hold on, count to 10, and measure the distance so as to get a slope." You'd look at the speedometer, which shows your speed at that instant. Moreover, you know the speedometer will show a different number a little while later as you try to pass a slow-moving truck. This is the concept behind instantaneous velocity, the velocity of an object at a particular instant in time. Keep in mind, in English, the word instantaneous just means really, really, really quick. But here we're talking about truly instantaneous, truly an instant in time. You can see how the English usage came out of this, but we should be careful here that we're not talking about just really quick or really high speed. We're saying, what is your velocity at some actual moment in time? How might you estimate the instantaneous velocity? Well, you might see how far your object travels in 1 second and compute the average velocity. But you know you'd do better to measure after only half a second. And it'd be even better to measure after, say, a thousandth of a second. In fact, you'd like to measure as small a time interval as possible. Mathematically, we say that the instantaneous velocity is the limit of the average velocity as we consider infinitesimal time intervals. And we write that according to this kind of weird notation, that v is the limit as the time interval heads towards 0 of the average velocity. And we symbolize that in calculus with this weird notation called dx dt. You might notice that it looks a lot like the delta x over delta t. The Greek letter delta, capital D, has become a lowercase Roman d, and that's cute because we're saying that delta t has become small. All of this is from calculus, though, and we don't use it in this class directly. If you're taking a calc class, this will look familiar, but if you're not, it's not a big deal. What we do want to say is we do act as if we take very small time intervals and see what comes up. Graphically, the instantaneous velocity is the slope of the line tangent to the xt graph. The tangent line pierces the graph at the moment interest, but the graph does not cross the tangent line there. In this graph, for instance, the tangent line is drawn at t equals 1. I should be very explicit, and I thought I fixed this, but I didn't, that this is a position time graph. And what we have here, the line tangent to the graph at t equals 1 second is shown. We would compute the instantaneous velocity by taking any 2 points on the tangent line. Not on the curve itself, but now on the line, and we would then find the slope between them. Illustrated here by saying, let's take 0 and 2 seconds, and so we take at 0 seconds the object is at, not the object, but the graph is at 2, and at 2 seconds the graph is at 3.8, and we find the slope of the line connecting them. Again, this comes down to saying we pretend for the moment that the velocity at that is frozen at that moment and has stayed constant. All right, it isn't, it's varying, but we say, what if it had been constant? What slope would it had to have had? All right. You might know the word tangent from math class, hopefully. In a math class, we have that if you have a circle, and then you draw lines that go near the circle, sometimes they miss, sometimes they hit twice, but sometimes, in a critical case, they'll hit, but only once. That's the tangent. These lines are called secants. These lines get no name. Lines that miss aren't particularly special. And the idea is you can see that if we draw the secant and we keep sliding over sort of to our lower right, eventually the secant becomes the tangent. Instead of piercing twice, we pierce once. This, we should be really careful. In geometry, they often define the tangent as the line that intersects the circle, but at only one point, we're going to use a somewhat more technical definition in calculus, and therefore in this class, because calculus is the language of physics. And we're going to say that a tangent line, or let's put it here, let's do first, a secant line is a line that crosses the circle, right? That pierces the circle, and the circle crosses over. If you're following along, it exists on both sides of the secant. But the tangent line touches the circle, but the circle is only on one side of the tangent. It doesn't ever show up in this region. And that's what we're going to use for our definition in physics via calculus. We're going to say a line is tangent to a curve if they intersect, but if at that location the curve does not cross over to the other side of the axis. A really important special case. When the xt graph has a maximum, the tangent line is horizontal, which means that its slope is 0. That's illustrated over here. That if the curve is going through a maximum point, then the tangent line will be horizontal. But that means that the slope is 0. And then, to remind you, the most important thing here, the slope of the tangent line is the velocity. So where the graph has a maximum, the object has a 0 velocity and therefore is at rest. It's not moving. At that instant, just before it was moving, and just after that it's moving again, but at that moment has come to rest. And if you think of this as an object moving along a line, the x has increased to some value, it's going to start decreasing, and before it can go the other direction, it must, at least for a moment, come to rest. Right? The same sort of applies if the curve has a minimum. All right, I guess I could illustrate that quickly. If we take a curve, and I'll just pick a random one. So here's our curve, and the tangent line, of course, at the minimum would also be horizontal, and therefore an object going through a minimum is also momentarily at rest. Keep in mind, and this will be very important, these relationships that maxes and mins mean at rest only work if the graph is a position graph, an xt graph or a yt graph. It doesn't work if it's a different type of graph. So don't let that get settled too much into your head. There's also one more kind of weird special case. If we think of something like this, where early on the tangent lines look like this, and they're decreasing in slope, and later the tangent lines are still positively sloped, but they've increased, then their slope goes through 0 at this moment. That's the so-called inflection point. It's a little weird. You can conceive of it, if you've been a driver, of what's called a rolling stop, where you pull up to a stop sign, but then you drive on through without really, you stop for the barest possible amount, and then you move on, and so your position would be, you do this like that. And so if I looked at your position, it would be stop, and then go forward again. And so here, it's neither not a max or a min, but v equals 0. And it turns out if you looked at the tangent lines, at first they would look like this, then it would go flat, and it would cross over once, and then like this. So it's consistent, but it's a little strange. All right, so look at this graph and pause the video for a second, and at least in your mind's eye, figure out where the tangent would be at 4 seconds, right? So 4 seconds is 1, 2, 3 at this point. Our tangent line, whoops, can be a little hard to freehand, but something like that. In the context of grading, not that that should motivate all your knowledge, but in the context of grading, since you're drawing approximately on graphs, people will grade with a lean hand, and they will not generally insist that you be really super accurate. But you could say that the slope of this thing, the speed of the object at 4 seconds, is going to be something like, if I take, how about we take this point and we take this point, then our velocity is, we started at 3 seconds, where the value of the tangent line is minus 3 meters, and we ended at 4 seconds, and the value of the tangent line looks to be 1 meter, and so we have minus 3 meters. Good. So my problem there is I need this to be positive. So let's clean this up. I'm just going to clean up my writing a little bit. we end at 3 seconds and minus 3 meters. And we started at, we started at 3 seconds, we ended at 4 seconds, and we ended at 1 meter. 1 meter minus 3 meters is 4 meters. 4 seconds minus 3 seconds is 1 second. So we get an approximate speed of 4 meters per second at 4 seconds. Same problem, says draw a line tangent to this curve at 1 second, and then we'll approximate the instantaneous speed there too. So pause the graph, pause and look in your mind's eye where you think it would be. We again want the line which touches at 1 second, but the curve doesn't cross, so it looks something, well, like that. And if I wanted to find the V here, oops, that's weird. We would say that we started, and I'm going to take, looks like it's 0 seconds, has minus 1/2 meter as its value. And let's go out to about 2 seconds. And it looks like that's at minus 4 meters. So that we get minus 4 meters minus 1 meter is minus 9/2 meters, minus 4.5 meters. 2 seconds minus 0 seconds is 0 seconds. So our velocity is minus 9/4 meters per second, which seems reasonable. All right, when do objects 1 and 2 have the same velocity? And then they give you some values. So pause and come up with your answer. We now want to start getting careful here. We want the same velocity. And velocity is slope of the tangent on xt graph, right? This is an xt graph, so we want the slope of the tangent. So they ask, is there ever a moment where object 1's slope is the same as object 2's slope? So then we think geometrically, well, what does it mean when two lines have the same slope? They need to be parallel. So is there a place where, right, so we're going to branch this out to being now, when is the tangent line of 1 parallel to 2? So looking here, I kind of want to grab a line that's parallel to that, but hits the curve once. To me, it looks sort of like in this region here. And we say, is it some instant before t0, at t0, some instant after, or both? Well, not both, because this tangent is getting closer and closer to 0, so it must be A. Just drawn up a little more carefully, and what I did there was literally in Google Images, just clone the line and slide it until it was tangent, which is the easiest way to do that.